ಇಲ್ಲ ಬಂದಿಲ್ಲ PPT. We have some, no. Welcome to VTU e-learning center. Yesterday in the session 1 on ARM embedded systems, we had discussed about the ARM philosophy and RISC design philosophy, and in the today's session let us discuss about the embedded system hardware and the embedded system softwares. Of course, like in the previous session we had introduced the embedded system hardware. So let me just use the same diagram which was used yesterday. So in the case of embedded system hardware, as we have discussed yesterday, we have a ARM processor and the controllers, peripherals and the bus. These are the 4 components which we have in the embedded system hardware, or specifically the ARM based embedded systems. The controllers are like the memory controllers, interrupt controllers and so on, and the peripherals which are like the real-time clocks, the serial UART and other peripherals which are on chip. These are the peripherals, and the bus is meant to connect all these 3 remaining components, that is the core, the controllers and the peripherals are all connected using the bus. Now let us look at each of these one by one. So ARM processor controls the embedded system device, and controllers coordinate the important functional blocks of the embedded system, and peripherals provide all the I/O capability external to the chip. The bus communicates between the different parts of the device, and the ARM core acts as the bus master, which is now the bus connecting all the devices, all the components are controlled by the ARM core. Now in the earlier processors, so like x86 based processors, we use normally a common bus called as the peripheral component interconnect bus, or PCIe is used. So this PCIe bus connects the video cards, the hard disk controllers and other things to the x86 processor bus or x86 processor, and this PCIe bus it is say external to the processor and it is a bus which is available on the board. So this type of technology is external or off chip, connects the external devices mechanically and electrically to the chip. Coming to the ARM embedded system, ARM based embedded systems, the bus technology is slightly different from what is being used on the x86 processor or PCs. Now embedded system uses a on-chip bus, because within the chip we have the peripherals, the controllers, the memory, all these are available on the chip. So therefore the embedded system uses a bus, or uses the bus which is definitely on chip, that is within the chip. It allows the bus will allow the different peripheral devices to be interconnected with the ARM core, and we find 2 different class of devices attached to the bus. The number 1 is the bus master, and number 2 is the bus slave. So as I said, mentioned earlier, the ARM core itself will act as the bus master. Then actually the bus slave are nothing but the devices which are connected to the bus other than the ARM core. So these buses naturally gets the directions from the bus master for any data communication. The ARM bus technology, so as we were mentioning, there are 2 things. The bus master, it's a logical device capable of initiating a data transfer with another device across the same bus. So naturally the bus slaves are again the logical devices which only responds to a transfer request that is directed by a bus master. So bus has 2 architectural levels, the physical level and the protocol. The physical level actually it covers the electrical characteristics and the bus width. The bus width actually it is decided by the type of processor core. Like for example, ARM many of the ARM cores are 32-bit processors. Naturally, the bus width will be fixed to 32, that is when the processor core is designed. Whereas similarly for 64 and other things, the bus width will change. Coming to the protocol, the logical rules are guided or given by the protocol, and it serves as the rules for communication between the processor and the peripherals, right? And the physical level, that is electrical characteristics of the bus are once again say decided, and say at the time of design, that is done by the silicon manufacturers, they decide upon the electrical characteristics, whereas the ARM has an IP license design which gives only the IP licensings. They give only the protocols, or they give the design of only the protocols. The ARM, we have a specific ARM bus protocols called as the AMBA bus protocol. The AMBA actually stands for the Advanced Microcontroller Bus Architecture, which in short we called as AMBA protocol or AMBA bus protocol. This AMBA was introduced for the first time in 1996, and the AMBA actually supports for on-chip bus architecture for ARM processors. The ARM processor or ARM came out with the two AMBA buses initially. Those two are the ARM system bus, which I have abbreviated as ASB, and the ARM peripheral bus, the APB. So this ARM system bus and ARM peripheral bus are the first set of bus that was introduced by the ARM, so called as the AMBA bus. Then later the another bus was introduced, was the ARM high performance bus, HB. So AMBA design can be reused with a different processor architecture. That means to say the AMBA design can be reused against the different projects, like when the processor core, new processor cores are designed, it is again not necessary to every time design the AMBA bus or AMBA protocols. So therefore the AMBA protocol can be reused with or is being reused with many of the projects. A peripheral can simply be plugged without having to redesign an interface. That is the beauty of the AMBA design. The ARM high performance bus AHB, it provides a high data throughput compared to ASB. So of course, like in the name itself we say that it's high performance bus, so therefore naturally it provides a higher throughput compared to the system bus, ARM system bus. So ARM system bus uses a bidirectional bus design, whereas AHB uses a centralized multiplexed bus scheme. So that is the main characteristics which has made the AHB to provide a higher throughput. The AHB allows the AHB to run at higher clock speeds. So the centralized multiplexed scheme allows the AHB to operate at higher clock speeds and naturally a higher throughput. The AHB supports data widths ranging from 64-bit and also to 128-bit also. In AHB we have two variants are available. The first one is MultiLayer HB. So the MultiLayer HB is a bus protocol which could be used with multiple processor cores, and we have another variant, that is AHB Lite. So these are the two variants of the AHB available, or ARM high performance bus available. So in case of MultiLayer AHB, it allows multiple active bus masters. That means to say, rather than having a single ARM core, so we can think of multiple ARM cores connected onto the bus. So we have several bus masters available, and the MultiLayer AHB supports same protocol for master and slave, similar to the normal AHB, but the MultiLayer AHB have different interconnects. This is the only thing which slightly modifies from the conventional AHB. So the MultiLayer AHB is suitable for systems with multiple processors, or in other words I can say ARM multiple cores. So the AHB, multi-layer AHB permits operations to occur in parallel. So since it allows for the parallel operation, that is the main reason why the AHB provides a higher throughput, and it allows higher throughput rates because of the multiple bus and the things and multiple higher widths. Coming to the AHB Lite, the second variant, it is a subset of the normal conventional AHB, in the sense like when I say like subset, it is not a full-fledged say AHB or ARM high performance bus. So it has limited single bus master and suitable for design that do not require the full features of standard AHB. So when I say like I have an embedded system application where I do not require all the features of the as normal standard AHB, in such case the AHB Lite will suffice our requirement. Let me again come back to the earlier diagram what we had shown, that is embedded system hardware. So in this let us again say summarize what all the buses that were used here. So this side we have the AHB arbiter, so which is directly connected to the ARM processor, and this side I have the high performance bus. The high performance bus is connected to the external bus through a AHB external bridge. So the AHB external bridge will allow to connect the high performance bus to the external bus which is off the chip or on the board. And the next category of the bus I have on this side is to connect the peripheral devices. So naturally I have a bridge here which is the AHB and APB bridge. High performance ARM high performance bus is bridged with ARM performance peripheral bus. So AHB and APB bridge we have. On this side I have the APB I have, that means a ARM peripheral bus I have. So in total in this embedded system, ARM based embedded system, I have three different category of the buses used: external bus, AHB and APB. In the embedded system hardware, say we normally use the memory. So sometimes we also have multiple layers of the memory used. So we have memory hierarchy, which is again quite commonly talked or commonly seen in all the processors of the day. So we have the memory characterized by the multiple layers of the memory available, and the hierarchy we find. So memory is characterized by the hierarchy, and it is characterized by the width of the memory and the type of the memory at each layer of the hierarchy or at each level of the hierarchy. So memory selection is based on the comparison of the cost, performance and power consumption. So naturally, say as we use a larger memory and the memory of higher speed, naturally the cost of the memory will go up, and so similarly the cost of the embedded system also will increase. So whenever we design embedded systems, we actually select a memory of exact requirement, we calculate and then use accordingly, or wherever the cost constraints are there, we always try to use the memory of say slower speed. In case if it is not for, if the system permits, we use the memory of slower speed also we think of. A smaller memory always leads to lesser power dissipation. Therefore the power consumption is also a matter or a characteristics which is to be considered while designing the memory hierarchy, or while designing the size of the memory and the type of the memory. All these things are based upon the comparison of the cost, performance and power consumption. All computers have some form of hierarchy. Say especially we find in the embedded system, say we find on chip memory and off chip memory. on-chip memory, as the name says, so within the processor chip we have different types of memory incorporated, and apart from that, wherever it is necessary, we also connect the secondary memory, or we connect the external memory, so which is normally on the board or off the chip memory are found. Another important say parameter or the type of memory is the internal cache. So in the case of memory hierarchy, we also find the internal cache which is within the processor core, or say sometimes in the PCs we find the cache of different layers or levels. We find L1, L2, L3 and so on. Most of the processors do contain L1 and L2 on the chip, and L3 will be off the chip. Now coming to the embedded systems, say internal cache are available in some of the embedded systems. In some embedded systems we say intentionally avoid using the cache and also the secondary memory. So whenever the internal cache is used, definitely it improves the overall performance. So the cache is placed between the main memory and the core, and it is used to speed up the data transfer. So since the cache will capture a specific image of the memory or segment of the memory, it captures and then holds it very close to the processor naturally, so it is capable of supplying the data at a higher rate. So that is what we find. The internal cache, say whenever the internal cache is used in the embedded systems, so we are going to lose the prediction of the execution time. Sometimes say due to the non-availability or the cache say data available in the cache, if it is not say immediately available, it is necessary to fill the cache from the main memory, so that the time taken to fetch the data to the processor will increase. So therefore it is difficult to predict the execution time in the presence of the internal cache presence, and the internal cache will definitely make us it is a undesirable characteristics for real-time embedded systems. So since the execution time is becomes say unpredictable, naturally this is a highly undesirable characteristics for embedded systems. So the overall when you say like the total size of the memory as available, normally we find that the main memory will range from few kbs, few hundred kbs to few hundred MBs, like example typically 256 KB to 256 MB, or secondary storage wherever I use it may vary from 600 MB to say 60 GB. So this is typically the size of the memory, main memory or secondary memory connected to the embedded systems. Coming to the memory width, which is also another deciding factor to be done while selection of the memory. So the memory width could be typically 8-bit, 16-bit, 32-bit or 64-bit. For example, many of the ARM processors are 32-bit processors, they have say byte or half word say configurations also. So in which case say for example ARM 32-bit processor, so if ARM 32-bit processor say operates on 8-bit memory or 8-bit data, so it takes 4 cycles to fetch 1 word of information, right? Because ARM is a 32-bit, that means a 4 byte of information is to be fetched. Naturally, in case of a memory whose width is only 8-bit, so naturally I have to access 4 accesses are to be made in order to fetch 1 complete word from the memory to the processor core. So therefore it takes 4 cycles, whereas a 16-bit memory width will take 2 cycles to fetch 4 bytes, and a memory of 32-bit wide will take only 1 cycle to fetch 1 word of information. So naturally, looking to this example, I can say that 32-bit memory is always best suited because it takes only 1 cycle, therefore throughput will be higher and I get a good performance. But sometimes when the cost is a factor, and say sometimes we may select 16-bit memory also, it again depends on the actual system that is being designed or under consideration. In case of ARM processors, we also have the instructions which are called as thumb instructions, and these instructions are 16-bit wide, and using a 8-bit memory it takes 2 cycles, and using 16-bit memory it takes 1 cycle, and using 32-bit memory it takes only 1 cycle. So quite obvious. So thumb instructions, preferably 16-bit memory would be better, because I can fetch each instruction in 1 cycle. So say before going to the next, say the memory width, after memory width I have types of memory that is being used in the embedded system or ARM based embedded systems. So we have the first type of memory, read only memory. It contains the image that is permanently set in the memory, and ROMs are used in the high volume devices that are static. That means once I fuse, I cannot modify that. Therefore, so the code that is static or will never change in due course of time. So such code can be, data or code can be fused into the ROM at the time of the actual manufacturing. So usually the ROMs are used to hold the boot code. That means to say the code that is necessary, initially necessary to make the processor to come to a state of executing the application program, or say running the actual operating system. So that I call it as the boot code, and ROMs are preferable to hold the boot code. Similar to the ROM, the advanced, we have flash ROM. So the flash ROM supports for read and write. So in case of ROM, it is supports only read, so no modification can be done, whereas flash ROM supports both read and write. But though it supports read and write, so the write actually is a slower process or slower operation on the flash ROM, whereas read will occur at higher rate, whereas write will take longer duration. That's why we said that slow to write. So such kind of memory, that is flash ROM, are not suitable wherever you find that the data is dynamic. That means as we progress, the data keeps changing. So such dynamic data cannot be saved in flash ROM, because every time we keep updating, say after few set of instructions are executed, so therefore it takes more time. Therefore the flash ROMs are not used for holding dynamic data. So erasing and writing are completely software controlled, which is one of the advantage with flash ROM, and the flash ROMs are most popular because it is used as an alternative for mass storage or secondary storage. So that is where we find the use of flash ROM. And coming to the RAM, so in case of the memory, the different types of RAMs are available. So apart from the RAM, conventional RAM, we have DRAM, dynamic RAM. So the most commonly used RAMs are the DRAMs. So they are lowest cost per MB. So the storage cost per bit is lower. Wherever the cost is the criteria, a DRAM could be selected. It needs a regular refreshing. Say DRAMs are, though it has advantage of lower cost, but we have a disadvantage that the content of the DRAM, say gradually it fades down. So therefore the electrical charge on the cell are to be refreshed at regular intervals of time. So therefore this is one of the disadvantage of DRAM, and it requires a separate circuitry in order to refresh the DRAM cells. So it requires DRAM controller. The next version of the RAM we have is SRAM, static RAM. So the static RAM is faster than DRAM, and it requires more silicon area. That means the hardware required is more. So each cell of the SRAM will take more number of transistors than compared to the other RAMs. So therefore that's why we said that. So it requires more silicon area, and since it is faster, naturally the cost is higher, and it is suitable for high speed tasks. And the next type of memory is the synchronous DRAM, or sometimes we call it as SDRAM. So it is, since I say like it is synchronous, so it has a characteristic that it can run at much higher clock speeds than the conventional memory. So naturally after the DRAM, so we have the next version is synchronous DRAM, SDRAM, so it can run at still higher speed, and it synchronizes itself with the processor bus. So naturally once it synchronizes with the processor bus, naturally the data transfer throughput will increase, and internally data is fetched from the memory cycle, pipelined and finally brought out on the bus in a burst mode. So when I say like pipelined, what I mean is like say the continuous flow of information or continuous bytes or several bytes can be say transferred in the burst mode. That means say one after the other in a form of pipeline operation, the data can be transferred. So that is one of the advantage of synchronous DRAM or SDRAM. And all this is possible because the SDRAM is again connected by a clock, so therefore, so in order to synchronize itself to the processor bus, we find that therefore, so it can work in burst mode, as well as it can be operated at a higher speed or with a better throughput. Another component on the embedded system hardware is the peripherals. So embedded system interacts with the outside world through the peripheral devices. So as we were discussing, we have several say peripheral devices or the I/O ports on the chip. Therefore, say each peripheral usually performs a single task function and may reside on chip, or we have the option of say connecting the devices or the I/O ports off chip also. And all ARM peripherals are memory mapped. That means to say you find that the address of the peripherals are mapped onto the address say map of the memory itself. That's why we call it as memory mapped say peripherals or memory mapped devices. So therefore the devices will not have a separate address space, rather it is mapped with the address space of the memory itself. So that is what one of the characteristics of ARM peripherals. And programming the interface is a set of memory addressed registers. So we find the registers, and these registers are having the address which are mapped onto the memory addresses. Therefore the devices are identified similar to a memory address itself. So these registers, through the registers the data transfer can happen. And the controllers are specialized peripherals. Controllers are specialized peripherals that implement higher levels of functionality with an embedded system. So in case of the controllers for the peripherals, again we have two types of controllers are available. So mainly the memory controllers and the interrupt controllers. Basically the controllers are it's a mechanism to connect these units to the core, and say for example the memory, the address translation and the memory selection, the specific data selection, it is the question that comes under the controllers. So coming to the memory controller, so it connects the different types of memory to the processor bus. So as we said, it connects a ROM, it connects a RAM, and so such a memory connection is possible only because a memory controller facilitates the connection of such say units to the processor core. And on every time when the power up, after a power up, that means a switched on, power is the processor bus is switched on, the memory controller is configured in hardware to allow certain memory devices to be active. Okay, and some memory devices must be set up by software. That means say every time when after the power up, it is necessary to configure some of the devices which is done by the memory controllers. So when using DRAM, for example, when using DRAM, so memory timing is to be decided after every power up. So similarly, the refresh rate to be set up. So these things are the things that are to be done. So every time the power up, the memory controller does this kind of operations. Coming to the interrupt controller, say the interrupts are basically a mechanism in order to facilitate the device to be connected to the processor core, and when a device requires attention, the peripheral device will raise an interrupt to the processor core, and once the interrupt is raised, naturally the processor gets interrupted, and the processor needs to execute a handler or a peripheral interrupt handler is to be activated and it is to be executed, or sometimes we also call interrupt handler as interrupt service routine we call. So such interrupt handlers are to be executed as an action corresponding to the interrupt raised by, or the request raised by, the peripheral devices. The interrupt controllers provide a programmable governing policy that allows the software to determine which peripheral can interrupt the processor by setting the appropriate bits in the interrupt controller. So interrupt controller, it has a register, so each bit of the interrupt controller can be set or reset. So based on the bit set in the interrupt controller, so the interrupt controller decides about the processor to be interrupted, or which devices, what type of interrupts can stop the processor execution, or the handler which is at present in execution, so whether to be say stopped or whether to be continued, or the request raised by the processor, the peripherals is to be ignored. All this is the concern of the interrupt controller. Coming to the ARM processor, ARM processor supports for two types of interrupt controllers. One is called as standard interrupt controller, and the next one is vectored interrupt controller. We have two types of interrupt controllers. So just to mention here, the 8086 we have in the earlier sessions module we have discussed about the vectored interrupts that is supported by the x86 processors we have discussed. So here a similar type of interrupt controller is available in case of the ARM processor also. Apart from that, it has support for a standard interrupt controller also. So these two types of controllers, or interrupt controllers, are available with the ARM processors. And coming to the SIC, the standard interrupt controller, it sends a interrupt signal to the core when an external device requests servicing, right? When an external device requests for executing the interrupt handler, in such event the controller will send a signal to the core indicating that a specific peripheral device requires a handler to be executed, and it is possible it can be programmed to mask an individual or a set of devices. So based on a priority can be assigned, and based on the priorities assigned, it is possible to mask an individual device request, or a set of device requests can be masked, or it can be say overlooked or neglected. So interrupt handler determines interrupt requesting device, which device is presently requested for the interrupt handler, the device handler that is to be executed. So interrupt requesting device, it determines by reading the device bitmap register in the interrupt controller. That means to say among the several peripherals connected to the processor. So each time when the interrupt occurs, it is necessary to find out which device has raised for the interrupt request, or which device is presently say trying to request the processor to execute the service routine. So that detection, or that is to be identified by the controller. So that is what we said, that interrupt controller in the case of SIC, so that is done by the bitmap register which is supported, right? And coming to the vectored interrupt controller, so the vectored interrupt controller are more powerful than compared to the SIC, for the reason that the vectored means say the device which is requesting for the interrupt will also specify, or there will be a means, a direct means to say communicate the device ID also to the processor. So the controller job is simplified, and so therefore we say that vectored interrupt controllers are more powerful, and the VIC prioritizes the interrupts and simplifies the determination of the interrupt causing device. That is what the second part I said, like the determination of the interrupt say or identification of the device causing the interrupt is made very simple in the case of the vectored interrupt controllers. And VIC only asserts an interrupt signal to the core if the priority of the new interrupt is higher than the presently executing interrupt handler. So that means to say a new interrupt comes, and if the priority of the incoming interrupt request is higher than the presently executing interrupt handler, then in such case the VIC has to assert this and then say make the change of the interrupt handler to proceed, right. So this is what the VIC does, and the vectored interrupt controller will either call the SIC handler or it causes the core to jump to the handler of the device directly. So whenever it calls for the SIC handler, naturally it gives the handler address, or sometimes the VIC itself will give directly the address of the handler routine to which the core can directly jump upon and then start executing the handler. So that is possible. So with this we have just discussed about the embedded system hardware. Now coming to the embedded system software, the ARM embedded system has the layered software architecture as we have indicated here. We have the hardware device on which we have a layer in which we have the initialization code, the device drivers, operating system, and the last outer layer is the application. So this is how the software abstraction layer executing on the ARM hardwares. And of course, like each layer we are using here in order to abstract the details of the hardware as well as the details of the underlying software layer. So embedded systems needs a software, fine, any system, whether it is a say embedded system or otherwise a PC, so they need a software to say run the application or to say find the solution to our problem. Embedded system needs software in order to drive the embedded system, and each software component in the stack uses a higher level of abstraction to separate the core from the device. That is what we found in the previous diagram. So this is what for the abstraction purpose, so the design is made so. And in the stack we have the first layer, which is immediately above the hardware device is the initialization code. So initialization code is specific to a particular target, because say it should have the details of the underlying hardware. So therefore we said that it is specific to a particular target or a group of target, and the initialization code set up the minimum parts of the board before handling the control over to the operating system. That means to say soon after the system is powered on, so the first software that runs is the initialization code, so which has to make some initial preparation or initial setup before the OS will take over. So that is what done by the initialization code. Then next we have it takes the processor from the rest state. That means every time when I switch on or power on, so it takes the processor from the rest state to a state from where the OS can take over or the OS can run. So that is what this initial handing over is done by this code, the initialization code. Usually it configures the memory controller, the processor caches, and initializes some devices. This is what the main responsibility of the initialization code. So first it has to configure the controller, memory controller, like we took the example of the DRAMs are to be initialized, such things are the main things that are done here, and the processor caches are to be initialized, and some minimum devices are to be initialized. And the initialization code handles the number of administrative tasks before it hands over the task or the control to the OS. So it has to initialize the hardware configurations, and it has to perform some diagnostic say tests, and it should say make the booting process or it should complete the booting process. So these are the main three phases of the tasks or administrative tasks that this code has. And the initial hardware configuration involves setting up target platform so it can boot an image. So this is what it does. For example, the memory system normally requires recognition of the memory remap. So memory remap means say every time when the processor say in the phase of boot up, so the memory configuration expected is slightly different, or a specific memory configuration is expected, but after the boot up, so the memory configuration will change according to the controllers that are present there. So therefore that is shown here. So this is what we have the setup before the say boot process initiates. So we find that the address 000 to FFF here. So starting from the address 000 we have the boot ROM mapped, and then we have DRAM large contiguous block, fast SRAM, and then IO registers and so on. But after that the memory configuration may change, so we find the fast RAM say, and then boot ROM. So this way, before we have some memory configuration, but after the boot up, so the configurations or remapping is done here. That is what the task of initialization code. The next the embedded software is I mean, like the task of the initialization code is diagnostic task. The diagnostic is, when I say like diagnostic, it is only to test whether everything is right or something has gone bad. So for that diagnostic task is very much essential. This particular code responsible for diagnostic task, it tests the system by exercising the hardware target to check if the target is in working order or not. And it is soon after the diagnostic task is run, so naturally fault identification or fault isolation can be easily done. So that is what we do here. And the last phase of the administrative task done by the initialization code is the booting. So booting involves loading and loading the image and handling the control over to the image. So it involves loading the image and say the code which is necessary for transferring the task control to the OS. So some part of the code is to be executed, and handing over the control over to the to that image. So through which the OS can, from there it can take on. So boot process itself can be complicated if the system must boot different operating systems. So if it is a single operating system, the process is simpler, or the booting process is simpler. Sometimes if the embedded system supports for multiple operating systems, then naturally the booting process becomes little complicated. So that is what we have listed here. The booting is the final phase of the initialization code. But first you load the image and then transfer that. Okay, loading an image involves copying an entire program or including the data into the RAM, and once booted that modifies the program counter, right. Once the booted, the program counter is to be modified to hold the starting address of the RAM from where the subsequent thing can take over, and then later it hands over the control to the operating system. So sometimes the image code is compressed. So every time if the image is compressed, naturally, so every time when it boots up, it is to be say uncompressed and then decompressed, and then the process should take from then on. So these are the different say the first initialization code and the actual say task of the initialization code. Let us discuss one more software component, operating system, which of course like you are all familiar with. So the operating system provides an infrastructure to control the applications and manage hardware system resources, and many embedded system does not require full OS, right. This is one of the important point here. Say depending on the application of the embedded system, sometimes a full-fledged operating system may not be required, in which case say a simple task scheduler itself could be could be sufficient, or it may suffice the requirement, in which case a lighter OS is used. A lighter OS, when I say like it has lesser functionality. So such operating system will satisfy the requirement of the embedded systems. And say the simple task scheduler which is either event driven or pole driven will be sufficient in such cases. And the ARM embedded system supports for more than over 50 operating systems. So which of them, these things can be categorized under the two things, that is real time operating system or platform dependent operating system. So in case of real time operating system, we have hard real time versus soft real time applications. So depending on the hard real time or soft real time, my operating system also will be different, or the design of the operating system will be different with respect to the embedded systems. Say hard real time always expects a certain event or the signal to be completed in a stipulated time exactly. So such requirement say is to be honored by the real time hard real time operating systems. In case of soft real time applications OS also, we have a similar requirement. Those things are to be done, but a slight marginal say overshoot or undershoot may degrade the performance, but however it is not a threat for the system. So that is what we have, hard real time and soft real time applications. So which normally based on that our RTOS, the real time operating system design also may vary. A platform dependent operating system is a conventional operating system, which of course like we have learnt. So such operating systems, ARM also supports for Linux and other operating systems, say it supports. The device drivers are part of the embedded system softwares, and these device drivers, the first and foremost requirement is they have to provide the interface, software interface to the peripherals on the hardware device. That is the first and foremost requirement of the device drivers, and they are application softwares. So performs one task. Coming to the application software, the application software performs one task required for a device. Software components can run from ROM or RAM. If the software runs from ROM, we call it as say sometimes the ROM code that is running, we also call it as the firmware. That means say the code which is always permanent, which will not change. So we call that as the firmware. So to summarize the session, say in this session we have discussed about the embedded system hardware, in which we have discussed about the 4 different types of components present in the ARM based embedded systems. We have ARM core, the controllers, different controllers, and the peripherals, and the bus. Again in the bus we said about 3 different types of bus. It contains so HB, ASB and APB we have discussed, and then also external bus. And we also discussed about the AMBA protocol. And coming to the embedded system software, we discussed about the layered architecture of the initialization code, and the device drivers are initialization code necessary for the system to boot up and make some administrative say processes or tasks to be executed is mainly responsible for. Device drivers provides interfaces, operating system again which supports for interfacing the hardware devices, hardware components with the user, and then application, and finally we discussed about the application. So nothing but the software which is responsible for the entire device to operate or work. So this is what we have just discussed in this session.